I'll take a look at these. Let's see. Okay. It looks like we actually got the first one incorrect because one of the pathways there is all of these are pathways that will happen in the test tube, but one of them is so minor that it'll happen such a small percentage of the time that you wouldn't be expected or desired to draw it or to keep it in your course. So
Okay.
which of these is the minor pathway?
Probably that middle one, that second one drawn
Mm-hmm.
right in here.
Let's see. Okay, and what's your reasoning there?
Because it has an extra step. It looks like it's a longer,
Okay,
slower
that's
reaction.
good to discuss there. That step now, is that step a reaction step or resonance?
Oh yeah, that's right. This would be a resonance, actually, like
So we
that.
probably should have drawn that resonance arrow there, which means the mechanism actually is not more steps, because
Okay.
resonance is not a step of the reaction. Remember that both resonance structures actually represent the same molecule. Both resonance structures represent the same molecule. Drawing an extra resonance structure doesn't add an extra step to the mechanism. How many steps are there in this mechanism?
There are 2 steps.
And that's true even for the third pathway. Even for the third pathway, there's only 2 steps. The resonance doesn't count as a step.
Okay.
Actually, what I was going for is that the first pathway is far less significant. It will occur far less often than the other 2. Can you see any reason why the first pathway is less important than the other 2?
Is it because there is no resonance in that intermediate?
Why would that make that less important?
That resonance allows for that final. Let's see. Trying to remember. The reaction moves faster, more stable. The starting reactants, and no, sorry, I'm mixing that up. So why would that affect it? I think I'm overthinking it and not coming to a conclusion.
Okay.
Yeah.
All right, well, let's
Sure.
review that. So this is something we've talked about in a couple of previous sessions. This is a problem from a couple of sessions ago. I gave you, I think, a homework question on this that we got incorrect previously, so it looks like this is a topic we're having some trouble with. Let's look at this again. So how many steps are there in this reaction?
2.
That's right. Which is the hard step? Which is the rate determining step?
I would say the first.
And how do you know?
Because there are no formal charges. When you're dealing with the formal charges, a positive and a negative charge, that would be a very, very quick and easy reaction. Whereas...
Which reaction would be quick and easy, the first one or the second one?
The second, where there are the formal charges.
Uh-huh.
But the first step, you're not dealing with formal charges, but you're dealing with delta or partial charges, and you're breaking a bond. Seems like that would require more energy and be a slower reactive step, slower step than the second.
Okay, that's on the right track. Let's try to clarify that, or give it a simpler explanation. One thing you said was that it sounded like you said the first step didn't involve any charges, and the second step did, formal charges. That's on the right track. Now, of course, in a sense, they both involve formal charges. It's just, in the first step is creating formal charges, and the second step is unforming formal charges, right? They both involve formal charges, but in the first step, the formal charges are in the product. And in the second step, the formal charges are in the starting material. Well, is it easier to form a carbocation or unform a carbocation?
Unform.
That's right. So which step is easier, the first or the second?
The second.
Okay. That's pretty much on the same that's kind of the same logic that you were just discussing. So your explanation was definitely on the right track, but you were maybe overcomplicating it. We can simply say it's easier. It's hard to. Is it hard or easy to form a carbocation?
It's hard to form a carbocation.
Yeah. So the first step is the harder one because that's the one that's forming the carbocation. Remember, we especially want to focus on the charges on the main molecule, so to speak. That's a concept we've talked about before. The first step. So that would be. I think that was what you were getting at before. So you were on the right track, but we could have simplified your explanation. The first step is harder because it's creating a carbocation. The second step is easier because it's unforming the carbocation. Okay, so which step should we focus on when we're deciding which path is favored? How are we going to decide which path is favored? By focusing on the first step or the second step?
The first step.
Because that's the rate determining step. Remember, it's the rate determining step that kind of determines the properties of the reaction. Just like we used this analogy before. If you're out taking a walk hand in hand with a toddler, if you want to know how fast the walk is going to be, it's not going to do any good to ask whether you're in shape and whether you're up for the walk. You need to focus on how the toddler is feeling because they're going to be determining the outcome. Okay, so we're focusing on the first step. Now, in which case is the first step the easiest? Or, I'm sorry, in which case is the first step the hardest?
In which case did you say?
Which of the three paths? Because remember, now we want to use the first step to decide which of the three paths is favored and which paths are unfavored.
Sorry, I just wrote a line for that, but I think in that first one, it would be the most difficult because there is no resonance to stabilize that positive, that carbocation.
Remember, our whole point was that the first step is difficult because it's forming a carbocation, but it's the most difficult in the first pathway because there's no way to because there's no resonance. Well, what's stabilizing the carbocation in the second path and the third path?
Resonance.
That's right. So, and we've seen that resonance is a pretty strong phenomenon. So usually when resonance is involved, we're going to focus only on the pathways that are stabilized by the resonance. So the first path is forming a secondary carbocation. Secondary carbocations are usually okay, but a secondary carbocation that's resonance stabilized is far preferable to one that's not resonance stabilized. So the first path would be so minor that we should cross it out. It's okay to write it down to start with so you can think about it. It's okay to write that path down to think about it, but then we need to cross it out because it's so minor. It's not one of the paths that the class would want us to keep. Okay, now this is an idea we went over in a couple of different sessions, and we had some trouble with this a couple of different times, so this is something to highlight and to go back and review, maybe rewatch this part of the video so we can get this down. because this has given us a little bit of trouble. Remember, the thing we've been focusing on for quite a few sessions is resonance. We've been trying to use resonance to explain things. I think we've been doing pretty well with that, but not with this particular example. This example has been giving us some confusion. What is it that's making this particular example so tricky? I'm not sure. It might be that because the logic actually has a couple of steps. First of all, you have to decide which step of the reaction to focus on, the first one or the second one, before you start thinking about the resonance. I think that might be one thing that's confusing us here. So remember, when there's a multi-step reaction, if you want to analyze the properties of a multi-step reaction, the first thing you want to do is decide which step to focus on. And we generally need to focus on the rate determining step. And the rate determining step is the one that has the unstable product or the unstable starting material?
The unstable product.
That's right. The product is more unstable in the first step because that's forming the carbocation. On the other hand, the second step is relatively easy because that has an unstable starting material, which makes for an easy reaction. So so the first thing is to focus on the first step, because that's the harder step, and then you ask, well, which of them has the least, and then you compare the first steps of the various reactions. Then we compare the first step. So maybe that's what is giving us some confusion, that the thought process goes through a couple steps as well. First, you have to decide which step of the reaction to focus on before you can decide which pathway is preferred. Okay, so in any case, it's important to see that resonance is favoring those two, the second and the third pathway there, because they're producing resonance stabilized intermediates. Okay, is that making sense?
Yeah.
Okay, good. Like I said, we've had some trouble with that. We've looked at this example a couple times, so that would be a good one to mark and review. Let's see. Okay, so I'll take a look at your answer for the second case. All right, so what role is the nitrogen playing in that step?
Base.
Okay. And what role is the other molecule playing?
Acid.
Okay. Would you call the NH3 a strong base or a weak base?
Weak base.
And how about the acid? Is that a strong acid or a weak acid?
That would be weak also.
So does that reaction seem like it's likely or unlikely?
Unlikely.
Okay, so does that look like it's correct or incorrect?
Incorrect.
Okay, so that's something to watch out for. Remember that we generally don't have weak acids reacting with weak bases. Now, like everything in organic chemistry, there are some exceptions. There are some exceptions to that I can think of. But you don't want to do that unless you have a specific reason to know that this is an exception. So I don't know if you thought about it in that light here. Is that negative charge on the oxygen resonance stabilized? That might change things. Is the negative charge on the oxygen resonance stabilized?
No.
No, it's not. There is no resonance there. So you might have been thinking that resonance would make this a stronger acid, but it doesn't work that way. Actually, there is no resonance stabilization after it loses the hydrogen. So, okay. So that reaction is not going to work. So generally, remember there are some exceptions, but generally weak acids don't deprotonate weak bases. So that reaction does not actually look reasonable.
Okay.
All right. So we'll have to come up with a different reaction. Let's see. So what role could we expect that nitrogen to play here besides base?
Nucleophile.
Okay, so let's try that instead. Who might be a reasonable electrophile here?
Carbon-1 would be.
Okay. Why would carbon-1 be a reasonable electrophile?
Resonance actually would bring the the pi bonds, shift them, I guess you could say. leaving carbon 1 as a in one of the resonance structures as a carbocation.
Good.
And that would be a good electrophile.
Okay, that's right. There's a resonance structure that puts a positive charge on carbon 1. Good. What other atom might be an electrophile?
Carbon 3 could be.
And why is that reasonable?
Because of the delta positive charge on the carbonyl carbon.
Okay, that's right. So we have a little bit of a difficulty here. It's not really clear whether carbon 1 or carbon 3 should be the electrophile. But when we actually studied this type of reaction in our previous session, and when we studied it, do you remember who did we say is usually the electrophile for this type of reaction?
I know we made a big point of carbon 1 because it was kind of a hidden carbocation, and so that we made special emphasis of it. But I'm not remembering if that was the more common one. But
okay, yeah. Yes. So we focused on carbon 1 because it was surprising it was the electrophile, but also because it turns out that it almost always is the electrophile. There's a couple of exceptions, but generally speaking, the large majority of nucleophiles in this situation would attack carbon 1, not carbon 3, which is the way you've started drawing it already. Okay, good. By the way, when you did these homework problems, did you do them shortly after our previous session, or you might have waited a while since it's been a while since our last meeting?
I actually waited.
Okay.
So
all right. So I think you might have actually started to forget quite a few of the ideas that we went over in the last session. It's actually, in some ways, it's okay to wait because it gives you a chance to review. The important thing, though, is remember the reason for doing the homework problems is to practice the material from the tutoring session. The reason for doing the homework problems is to practice the material from the tutoring session. So there's no point doing the homework problems unless the tutoring session is crystal clear in your mind. The first thing you want to do when you sit down to do the homework problems is ask, is the tutoring session crystal clear in my mind? If it's not, you need to review the tutoring session before you do the homework problems. So you might do that by reviewing your tutoring notes, or if necessary, by rewatching the video. Otherwise, you don't get much from doing the homework because you end up just kind of, you end up not using the techniques from the session. So remember to always try to make sure that the session is very clear in your mind, doing whatever it takes to do that when you're doing the homework problems, because the whole point of the problems is to practice that material. Okay, so here we have these. Now, what you've drawn here is definitely one possibility. Okay, good. So let's draw. So you have your arrows.
Mm-hmm.
So when you're attacking carbon 1, that's going to, you need to move the pi bond out of the way to attack carbon 1. So where are you going to put the electrons from carbon 1? Well, one place you could put them is on the oxygen. You have the electrons moving all the way from carbon 1 to the oxygen. That's perfectly fine. However, that turns out not to be, I think, the most useful resonance structure to draw. Instead, something else we covered previously is that it's more useful to put the electrons where? That's right. That turns out to be a more useful resonance structure. It's not always the one that's drawn in class, but I think it's the best one for a beginner to draw. So let's go ahead and draw the product from that step.
Okay. Okay.
All right. Okay, good. Any idea what happens next?
Well, I suppose Be great if we could have that negative charge grab a hydrogen from nitrogen. No, I'm not quite sure what would happen next.
Take a guess.
Well, we just had a nucleophile attack an electrophile, so we could have a acid-base reaction.
Good.
I don't know if this would be an intramolecular possibility to take care of the problem all at once, but if not, then we could have the NH3 act as a weak base on that strong acid there and pull away a hydrogen.
Okay. All right. So that's a fairly good analysis. That certainly is one possibility. That certainly is one possibility. In this case, I think it's best to actually go with your first choice, though, and do the intramolecular reaction.
Okay. So I'm not sure if it would be best for that carbon-2 to grab that hydrogen, or if that oxygen would be best to grab it. But supposing you did have that carbon-2, then that would get rid of the positive and the negative charge. And that would be the product.
Does it look like we're done, or that we need another step?
Looks good. Looks done.
Because there's no charges left. Okay,
Yeah.
good. Okay. So this is probably the best way to draw this reaction, although you might see it a couple different ways in the textbook. There's a couple different ways the textbook might draw this, but I think this is the best for a beginner. One thing you said that was good is you said that since we started with a nucleophile-electrophile reaction, we would expect the next step to be acid-base. So that was a good point. And here we can just use the negative charge as the base and the positive charge as the acid. One thing that might have made you a little uncomfortable with this is we have seen that oftentimes when there's two formal charges in a molecule, you end up only using one in the reaction. I don't know if you were thinking about that. In the past, oftentimes when there were two formal charges in the molecule, we ended up only using one in the reaction. But this is an exception to that. In this case, we're going to use it's probably best to use both of them to get rid of both charges at the same time. If you hadn't done it that way, you could have kind of done this in two steps. You could have had an outside NH3 get rid of the charge on the N+, and then you could have had that NH4 plus get rid of the charge on carbon-2. There's probably a couple different ways this could happen in real life, but on paper, this is probably the best way to draw it. Now, one thing you mentioned was that you weren't quite sure whether the proton was going to end up on carbon-2 or on the oxygen.
Yeah.
That was an interesting point. Why would the oxygen be acidic? I mean, be basic. Why would the oxygen be basic? I can see why carbon-2 is basic because it has that negative charge. But why would the oxygen be basic?
I guess it makes sense that carbon-2 would be more basic because it has a formal negative charge, whereas oxygen only has a lone pair of electrons, leaving it as a weak base.
Okay. All right. Well, now we're getting... so that wasn't quite on the right track. Now, It turns out that carbon-2 is more basic, but remember there's another resonance structure where the oxygen has the negative charge.
Okay.
I thought that was what you were thinking about.
Yeah, that is what I was thinking.
Okay, maybe I'm confusing you a little here, but remember there are two different resonance structures. There is another resonance structure where the oxygen has a negative charge.
Yeah.
But do you remember what's the name of this molecule with the negative charge? This is something we talked about quite a bit in our last session, or maybe the last two sessions. What's the name of this molecule with the negative charge on carbon-2, or on the oxygen?
Enolate?
That's right. It's an enolate. That's one of the key types of molecules we've been talking about. We talked about how there's two different resonance structures for an enolate. one where the negative charge is on carbon-2, and one where it's on the oxygen. By the way, what's the name of carbon-2?
The alpha carbon?
That's right. We talked about how when there's a negative charge on the alpha carbon next to a carbonyl, that's called an enolate. But there's another resonance structure where the negative charge is on the oxygen. Now, remember that it's hard to figure out from first principles who's going to be more reactive then, or who's more likely to react, the alpha carbon or the oxygen. Did you remember, who did we say actually usually does the reacting though? Who's usually going to be the nucleophile or base? The alpha carbon or the carbonyl carbon in an enolate? That's just something to memorize. Do you remember what we said about that?
The alpha carbon.
The alpha carbon. That's why remember earlier you were going to draw the resonance structure where the negative charge was on the oxygen. And I said it's probably better for a beginner to draw the resonance structure where the negative charge is on the alpha carbon. The reason I said that is because it's the alpha carbon that usually goes through the reactions in your course.
Okay.
Okay. So again, this is some material that you might have forgotten from the previous session. But an enolate has two resonance structures. The negative charge could be on the alpha carbon or on the oxygen. But usually, who's going to react in the next step? Who's usually going to react to the enolate, the alpha carbon or the oxygen?
Alpha carbon.
Why? Why? Well, we didn't say why. That's just something to memorize. You can't really figure that out. We just memorized that it's usually the alpha carbon that's going to react in an enolate. So which resonance structure is probably better for a beginner to draw? The one where the negative charge is on the alpha carbon or the one where the negative charge is on the oxygen?
On the alpha carbon.
That's right. Now, this is a little confusing because instructors often draw the negative charge on the oxygen. Instructors often actually prefer to draw the negative charge on the oxygen, but they're both right, and my point is that for a beginner, it's better to put the negative charge where it will show the reactivity. So we're showing the negative charge on the alpha carbon to show the reactivity more clearly, even though textbooks sometimes draw it either way. They might prefer to draw the negative charge on the oxygen. Okay. So that was important here to see why carbon. How did we know that carbon-2 is going to protonate and not the oxygen? Well, we just kind of memorized that it's usually the alpha carbon that goes through the reaction in an enolate. So for that matter, notice that in the first step we put a negative charge on carbon-2. In the first step we put a negative charge on carbon-2. Carbons generally don't like having negative charges. So why were we able to put a negative charge on this carbon when we normally don't put negative charges on carbons?
Resonance would stabilize that negative charge.
Yeah, it's just another way of looking at what we've just been talking about for the last few minutes. Okay, so we had some issues with this. How about carbon-1 that was electrophilic? What's the name we gave to carbon-1?
That's the beta carbon.
That's right. So what we talked about in our previous session, we saw that in conjugated carbonyls, the beta carbon is electrophilic. Why is the beta carbon electrophilic in conjugated carbonyls?
Why is the beta carbon electrophilic?
Right.
Because it has resonance, revealing a resonance structure with a carbocation on the beta carbon.
Right, as you'd already explained earlier, so that's good. Of course, the carbonyl is still electrophilic, so again, that's something you can't figure out. You just have to memorize who is usually going to act like the electrophile in a conjugated carbonyl, the beta carbon or the carbonyl carbon.
The beta carbon.
Why? Why? Well, I didn't tell you why, but it's just something we memorized. Sometimes there's some stuff in organic chemistry, so we can understand why the beta carbon is electrophilic based on resonance. But there's also a bunch of stuff in organic chemistry you just have to memorize. We're just memorizing that it's usually the beta carbon that's the electrophile. There are a few nucleophiles that prefer the carbonyl. You might study those later in your course, but most nucleophiles attack the beta carbon. Okay, so that's what we did here, and we saw that usually after you do your nucleophile electrophile reaction, you usually do an acid-base reaction. And it's usually best when you're drawing the enolate to put the negative charge on the alpha carbon, because usually that's what's going to react next. Okay, so that reaction gave us some trouble too. This is a reaction you might have forgotten. Going back, remember that at first we got off on the wrong foot here, because at first you were trying to do an acid-base reaction. Well, why did you do that? Why did you try to start with an acid-base reaction? Well, I think it might be because you got a little mesmerized by that hydrogen. Well, why would that hydrogen mesmerize a student? Because it's very unusual. Most hydrogens are not drawn, right? After all, there's tons of hydrogens in that molecule. there's hydrogens on carbon 1, carbon 2, and carbon 2. Why didn't you take any of those hydrogens? Well, just because they weren't drawn, maybe. They were treated as hidden hydrogens and they weren't drawn. But the hydrogen on the carbonyl was drawn, and it might just have attracted your attention. You might have thought, oh, you might not have thought this consciously, but unconsciously you might have thought that's important because it was drawn. That's unfortunate. It's just usually when there's a hydrogen on a normal carbon, it's usually not drawn. It's usually treated as a hidden hydrogen. But when there's a hydrogen attached to a carbonyl, the convention is to draw it.
Okay.
When there's a hydrogen on a carbonyl, the convention is to draw the hydrogen. That's actually kind of an unfortunate convention because it makes it seem like the hydrogen is important. But it's a completely unimportant hydrogen. In fact, that hydrogen never does anything. I don't think there's a single reaction in organic chemistry where the hydrogen on the carbonyl ever does anything. But it tends to fool students into thinking something's going to happen just because it was drawn, and the hydrogens on carbon 1 and 2 were not drawn. So that might have been the unconscious thought process that went through there. So, by the way, when there's a hydrogen connected to a carbonyl, that's called an aldehyde. I don't think we've really talked about that name for functional groups before. But when there's a hydrogen connected to a carbonyl, that's called an aldehyde. So that's the aldehyde hydrogen. Students often think the aldehyde hydrogen is important because it was drawn, but it's completely unimportant. Remember I was just saying there is no reaction in the entire course that involves the aldehyde hydrogen connected to the carbonyl. It's unfortunate maybe that it's usually drawn because it makes it seem more important than it really is. Okay.
Okay.
Notice that the hydrogen that actually ended up being lost was on the nitrogen eventually. Let's see. So that's something to mention here. That might have been one reason why you did the acid-base reaction first, because you saw that hydrogen. That might have made it look more acidic because the hydrogen was drawn. So you might want to keep in mind that those aldehyde hydrogens connected to carbonyls are not actually important in any reaction.
Yeah.
Okay, so those both give us some trouble. Those are both important things we've covered previously. Remember again, don't do an acid-base reaction unless you have both unless one of the between a weak acid and a weak base, or at least you usually shouldn't. There's some exceptions to that, but that's usually a danger sign. Okay, well, let's see how we did on the remaining questions. Let's take a look at number 2. Okay, your answer for A is correct. Your answer to A is correct. It's not quite the way we described it in our session, though, so let's see if we can apply some of the ideas from our session, although your answer is correct and your explanation is correct, too. If that first molecule was going to act like an acid, which proton would it lose?
There's no preference. They're all equal.
So which proton could it lose?
Any of them.
Yeah. Well, just go ahead and draw a proton that it might lose. Does that hydrogen have a delta positive?
No.
Why not?
Hydrogen and carbon, they have basically the same electronegativity.
Good. We haven't talked about that for a while. That's good that you remembered that. Good. So, the explanation you gave here was actually a pretty good one. We have said that delta positives make things acidic. So that would be a good explanation for why the OH hydrogen is acidic and the other one isn't. So that's a perfectly good explanation. Let's also try to explain that a little more, though, using the ideas we talked about. So if you remember, the way we talked about this is we said, so the confusing thing is we said there's 2 ways to judge an acid, how acidic something is. You can do it by comparing the molecules before they lose the proton, or you can do it by comparing the molecules after they lose the proton. You can judge acidity by comparing molecules before or after they lose a proton. And sometimes one approach is best, sometimes the other. Which approach did you use here? You decided to use the approach where you compare the molecules before they lose the proton. Here you compare the molecules before you lose the proton. And like I said, your explanation is a good one. Your explanation is correct. The way we discussed this last time, though, was in this case, we compared the molecules after losing the proton, I think. Anyway, for practice, let's look at it that way, too. So how would you compare the acidity of these molecules by comparing the molecules after they lose the proton? How would that analysis go?
Well, in either case, once that hydrogen is taken by a base, the bond will be broken, and the electrons from that bond will then be received by the acid. In this case, it would be the carbon right there, and in this case, the oxygen would receive those electrons, and an oxygen, being more electronegative, is able to it likes the electrons more. It I guess could handle a negative charge much better than a carbon could handle that negative charge.
So far, so good. So which one does that say is more acidic?
It says that the oxygen is, because the more stable the products tends to be the more favored reaction.
Okay, good. That's right. So that logic is a little complicated, isn't it? If you remember in our previous session, when we went over this, we talked about how this is kind of subtle logic. It's kind of a long sentence or couple of sentences. You have to say, well, the second one is more acidic because after it loses its proton, the negative charge that it gains will be more stabilized because it will be on an oxygen rather than the carbon. And the oxygen is more electronegative, which makes it easier for it to handle the negative charge. And that means it was easier to lose the proton in the first place. So it's kind of a long chain of logic, but you basically went through that. You went through that long chain of logic. That is a kind of a long chain of logic, but it's a very important chain of logic in the ochem class. So we reviewed it quite a few times because instructors really want you to understand that logic. Okay. That's basically what you were saying. So your explanation was correct. Okay, so like I said, the answer you wrote down is perfectly fine. The answer you wrote down was correct. I think you would probably get full credit for it, but I wanted to review the other approach as well because that's an important type of logic in the course, and it's what we were focusing on last time. So what we saw is that when you're trying to ask who's more acidic, sometimes it's more convenient to focus on the acids before they lose the proton, but sometimes it's more convenient to focus on the acids after they lose the proton. In this case, you can either figure out the answer either way. In this case, you could focus on before or after you lose the proton. That's why I said your answer is certainly correct. Although usually, actually, for this case, the textbook would probably focus on the second way, but I think you would get credit for the way you thought about it. Okay.
Okay.
So that's important to review. So let's take a look at part B. Let's see. So I noticed one thing that you did that was good here is you noticed that they asked you to rank the molecules in decreasing acidity. So number 1 is the most acidic. It's good that you read that question carefully. The numbering would be completely different if they asked you to rank the molecules in order of increasing acidity. That's something to really watch out for when you're taking the DAT or that ACS test you're going to have as your final. Okay. Oftentimes people miss those multiple choice questions, or even just questions in their class because they don't pay attention to the words increasing or decreasing on this type of problem. So let's look at B. It looks like you did that, thought about that. Let's see here. Okay. Okay, this explanation is correct. You use that term induction, which we talked about last time, so that was a good use of that concept from the tutoring session. Now, your explanation here, I can see why that explains why 2 is more acidic than 3, because 3 doesn't have any oxygens. Can you be a little more specific? Why is 1 more acidic than 2?
Because there are 2 of those electronegative oxygens surrounding this alpha carbon right here, so it not only has one oxygen that affects it, but 2 that are affecting it, leaving it much more positive, much more acidic than the alpha carbons on this molecule number 2.
Good. Do they give it a positive formal charge or a delta positive charge?
Delta positive charge.
Right. Now, they're not actually attached to the alpha carbon. So this is kind of an unusual delta positive that we haven't talked about very much. But there's still small effects even on carbons you're not attached to. So the alpha carbon here will have a small delta positive and a slightly bigger from one carbonyl oxygen and a slightly bigger delta positive from another one. Good. So that's the one thing that was left out of your explanation here. You didn't quite say how the electronegative oxygens make the alpha carbon more acidic. So you might have said the electronegative oxygens make the alpha carbons delta positive by induction. That might have been a little bit better. The electronegative oxygens make the alpha carbons delta positive by induction. And when something has a positive charge, does that make it more acidic or more basic?
More acidic.
That's right. That's something we've talked about quite a bit. So you might have split this up into two steps. The electronegative oxygens make the alpha carbons more delta positive by induction, and positive charges make things more acidic. Okay, but I think that's what you were thinking. So that was a good explanation. Now notice again, you analyzed these by asking what they would look like before they lost their protons.
Yeah.
Now this explanation is correct. I'm not sure you would get full credit for this though, because it's probably not what the instructor would be going for here.
Okay.
Even though this explanation is correct, it's not maybe what the instructor would be going for, so they might or might not give you full credit. So let's look at another possible explanation here. What's another way to analyze number B?
Well, it would deal a lot with resonance. If you were to take a hydrogen away from any of these, then what you would be left with is a negative charge on the carbon which lost a hydrogen. And of course, a plain carbon does not want that negative charge all to itself. And in this case, molecule number 2, that negative charge could be resonance stabilized with that oxygen. And so that makes it a preferred, more stable product, making that reaction go more easily, which would result in a stronger acid than the molecule number 3. But then this molecule number 1, it would actually have more resonance structures, which typically is more stable. It has two carbonyls, one on either side, which it could resonate that that negative charge with, and spreading that, stabilizing that much better than the other two molecules.
Which makes it easier to lose the proton in the first place.
Yeah.
Okay, good. All right. Yeah, so that's that kind of long, convoluted logic that we ended up using for A as well. Or in this case, maybe it's even a little bit longer. But the point is, it's easier for carbon 2 to lose a proton. It's easier for the molecule you marked as 2 to lose the proton than the molecule you marked as 3 to lose a proton, because after it loses the proton, carbon 2 can stabilize the negative charge by resonance. And it's easier for the molecule you marked as 1 to lose a proton than for the molecule you marked as 2 to lose the proton, because after the one in number 1 loses the proton, it has more resonance structures to stabilize the negative charge. So the negative charge is happier in that molecule. Okay, so that logic you gave is correct. Okay. So notice that relied on resonance. When there's both resonance and induction, which is usually more important, the resonance or the induction?
Resonance.
That's right. Usually resonance is more important than induction. So actually, you probably would not have gotten full credit for the explanation that you gave. Even though your explanation is kind of correct, it's not really what the instructor would be going for, because it's kind of a minor factor. Compared to the resonance, the induction is a pretty minor factor. It doesn't really explain, it doesn't really show why the alpha carbons are so much more acidic in the second and the third molecule here. So this would not be a full credit answer. We have to use the resonance explanation here. Okay, so remember that's the main thing we've been working on for the last few sessions is resonance. Usually when resonance is involved, that's what the instructor wants us to use in our explanation. That's usually more important than induction. So there would be some induction here, and it complements the resonance, but it's less important than the resonance. Okay, so we didn't quite see what this question was going for, although you did get the right ordering using induction here. Okay, so we discussed that example, so I'll take a look at C. So you wrote down the correct functional group names here. Do you have more explanation off to the side? Yeah, okay, good. Okay, so I think you're saying that the second molecule is more acidic than the third because there's a resonance structure where the oxygen has a positive formal charge. Or maybe a bunch of resonance structures where the oxygen has a positive formal charge. Okay, so that's basically the right explanation there. Now, for the carboxylic acid, you wrote down that number 1 is a fairly strong acid. That's true. Is carbon 1 a strong, so is the first example, is it a strong acid in absolute terms?
No.
No. I don't know if we've talked about this, but strong and weak have both absolute and relative meanings. Carboxylic acids are not strong acids in absolute terms, but they're stronger than many other organic acids. So in that sense, they're strong. They're strong relatively. I don't think you quite gave an explanation, though, for why carboxylic acids are strong acids. Why would the carboxylic acid here be a stronger, why would the carboxylic acid be a stronger acid than the alcohol? Let's just compare the carboxylic acid and the alcohol. Why would the carboxylic acid be a stronger acid than the alcohol?
Resonance would help. Once that hydrogen is lost and the electrons are received as a formal negative charge on the oxygen, the carboxylic acid then can spread out that negative charge through resonance with the neighboring carbonyl, whereas the alcohol could not spread out that negative charge but would have to hold it.
Okay, good. That's right. Now, actually, I notice here that when you were looking at the phenol, you analyzed, remember again, there's two ways to judge acidity. You can judge acidity by what the molecule looks like before it loses the proton, or you can judge acidity by what the molecule looks like after it loses the proton.
Mm-hmm.
In this case, you ended up using two different methods. The method, when you were looking at the phenol, it looks like you were thinking about resonance before it lost the proton. It looks like for the phenol, you said that before the phenol loses the proton, there's a resonance structure where the oxygen has a positive formal charge, and that makes it acidic. But then when you analyze the carboxylic acid, you analyze the resonance after it loses the proton. There's nothing wrong with that. They're both correct. I just wanted to point that out. You could have analyzed the carboxylic acid the same way as the phenol. Before it loses the proton, there's a resonance structure where the oxygen has a positive formal charge, and that also makes it acidic. Okay, but anyway, your explanation was correct. Your explanation was correct. So that explains why 1 and 2 are more acidic than 3. And why is 1 more acidic than 2? Well, I can see now what you wrote down. You just said we just got memorized that carboxylic acids are stronger acids than phenols. That would be a little hard to figure out. So I guess that's fair. You basically said we have number 1 is memorized, that number 1 is stronger than phenols. Maybe it's because the negative charge in the carboxylic acid, all the resonance structures put the negative charges on oxygens. Whereas in the phenol, some of the resonance structures put negative charges on carbons, which might be less favored. But maybe it's just best to kind of memorize that. Okay, so it looks like actually, it looks like this one you gave some good answers. You gave basically the correct answer. I just wanted to point out that the carboxylic acid also has resonance going on here, just like the phenol. So that explains how we would compare both of them to the alcohol. But to compare that carboxylic acid to the phenol, maybe we should just memorize that. Okay, fair enough. So I'll take a look at number 3. All right, that's an enolate. I'm not quite sure if you answered the second question here. Why is it called an enolate?
Oh, no, I didn't answer that. It is, what was it? It looks like something else. It looks like, well, one of the resonance structures puts this negative charge into a pi bond between carbons 1 and 2. And that would explain the -ene for alkene. Right there. It's about as far as I can remember. Maybe I'm thinking of enol. That may be what I'm thinking of, because an enol seems like it just would have an alkene and an alcohol. That would have enol. And because of its similarity with that, it's called an enolate. I'm not quite remembering.
Okay. Now, you actually pretty much ended up with the exact right explanation. Well, your confidence fell pretty low there at the end, but your explanation at the end was pretty much exactly correct. It's called an enolate because it looks so similar to an enol. It's called an enolate because it looks so similar to an enol. In fact, it's just a deprotonated enol.
Okay.
If you can compare them, you can see that the enolate is just a deprotonated enol. If that enol lost its proton, it would look like the enolate. That actually is pretty much the explanation you came up with. You came up with the right explanation. You just weren't very high confidence about it. Turns out that enolates are one of the most important types of molecules in the second semester. So we're basically getting a head start on that material here. Enolates are a very important type of molecule, and I just wanted to review why they're called that. It's because they look so similar to enols. Now, the point here is the resonance structure I drew at the beginning doesn't look very similar to an enol. So you just have to memorize it has another resonance structure that does look similar to an enol, so they're both called enolates.
Okay. Now the ate suffix, is that typical for deprotonated state?
Yes.
Okay.
That's typical for when there's negative charges on oxygens.
Oh, okay.
When there's a negative charge on an oxygen, that usually ends in ate.
And so that would explain sulfate and sulfonate.
Excellent. That's good that you thought about that. Yes, that's just what I wanted to mention. We've talked about sulfates and sulfonates. So, for example, what's the name of this molecule?
Hydrosulfuric acid. Maybe not hydro, just sulfuric acid.
Just sulfuric acid.
Yeah.
After it loses a proton, it would look like this. Do you remember what we said is the name of this molecule?
Is that sulfate? Oh, hydrosulfate. Sulfuric acid. And then it's hydro. Oh, hydrogen sulfate. Okay.
I don't know if you remember this concept from your general chemistry class. Sulfuric acid is actually what's called a diprotic acid. Sulfuric acid is a diprotic acid because theoretically it could lose 2 protons. That doesn't actually happen in ochem. This is general chemistry. That doesn't happen in ochem. If it lost 2 protons, then it would just be called sulfate. So you can see why we have to call this hydrogen sulfate to distinguish it from regular sulfate. Okay, well, we don't need to go into too much detail here. The important thing is that the negative charge on the oxygen makes it called sulfate. When there's a negative charge on the oxygen, it's called the sulfate. Also, we've discussed this type of molecule. What type of role does this oxygen tend to play?
Leaving group?
That's right.
And that's toluene sulfate.
Say that one more time.
Toluene sulfate, is that right?
Now, this is actually called sulfonate. You were saying that correctly earlier,
okay.
But this is called a sulfonate. I'll draw it this way because this is easier to draw. This isn't too important. The difference between sulfates and sulfonates is sulfates have 4 oxygens. sulfonates only have 3 oxygens.
Okay.
So this is a sulfonate because there's only 3 oxygens, whereas this is a sulfate with 4 oxygens. And actually, this is a little confusing. Even though this doesn't have the negative charge yet, it's still considered, this is called an alkyl sulfonate. Why is that a logical name, alkyl sulfonate? What does the alkyl refer to?
The carbon chain.
Yeah, connected to the sulfonate. This a little bit contradicts what I was just saying, because in this picture that oxygen doesn't have the negative charge yet, but it's still called a sulfonate because it will have the negative charge after it leaves. So generally speaking, 8 refers to oxygens with negative charges, or in this case, an oxygen that will have a negative charge. That's right. So those are 2 examples that we've already seen. Another example, do you remember what the name of this type of functional group is?
Was that a carboxylic acid?
That's right. I think that's something we were just reviewing in the homework questions. Well, what do you call it after it loses the proton? I don't think we talked about that.
With 8.
Say again?
Something with an 8.
Excellent. That's right. Something with an 8. It's called
carboxylate?
Say again?
Maybe carboxylate?
Exactly. Exactly. That's right. So after it loses the proton, it's called a carboxylate.
Okay.
Because now there's a negative charge on the oxygen. So when there's negative charges on oxygens, that generally gets that 8 suffix. What's the name of this type of molecule?
An enol.
This is only a weak acid, but if it did get deprotonated, what's this called?
And we'd be back to our enolate.
That's right. It's called an enolate because there's the negative charge on the oxygen. Although actually, remember, there's another resonance structure that makes it hard to see why it's called an enolate. This is also called an enolate. This seems to contradict what I just said because now the negative charge is not on an oxygen anymore. But it's still called an enolate because there's a resonance structure where there is a negative charge on the oxygen. Okay, so yeah, 8 generally means negative charges on oxygens. That's just a little digression, but that's good to know.
Okay.
All right. Let's see, where were we? Okay, so this is an enolate. What role would you expect this to play? Oxygen and C2 are basic and or nucleophilic because of the negative charges. Good. What's the name for carbon-2?
The alpha carbon.
Good. So we could say, and more generally, the oxygen and the alpha carbon are basic or nucleophilic, but in this case it would be C2, so what you wrote down was correct. Now, you did a little quick sketch here to show the resonance structure for the enolate. And you got a little lazy there and you didn't number all the carbons. And notice that when you didn't do that, you actually ended up inventing a fake carbon because you didn't draw in that hydrogen. So that's one of the reasons why it's important to always force yourself to number all the carbons, because otherwise these pesky little careless mistakes creep in. Notice that hydrogen there is the one I was just warning you about earlier. That's that pesky hydrogen connected to a carbonyl carbon. That really tends to mess people up. We talked earlier about one way it messes people up. People think it's more important than it really is. But another way it messes people up is they forget to draw it. And if you don't draw it, but you still draw the bond, then you've accidentally invented a whole extra carbon. So again, that's the kind of aldehyde hydrogen I was warning you about earlier. Remember that one of the key topics in the second semester is carbonyls. One of the most important types of carbonyls is aldehydes. Aldehydes are a carbonyl connected to a hydrogen, and we've seen you really got to watch out for that aldehyde hydrogen. It looks important, but it isn't. But if you're going to draw the bond, you have to draw the hydrogen. Okay, so that's something to watch out for. That was just a careless mistake. All right, so that you were just drawing a quick sketch there. All right, so in any case, just to make sure that's correct in your notes, you said who the reactive atoms here. That's good, but we need to take it a little bit further. What you have down here is that it seems like either the oxygen or the alpha carbon could be reactive. But that's not quite good enough. Who is probably actually going to be reactive in the reactions you're going to see in your course?
Probably the alpha carbon.
That's right. That would have been a good thing to add then for your answer. Although theoretically they could both be reactive, most reactions in your course will use the alpha carbon. Most reactions in your course, the large majority, will use the alpha carbon. So which resonance structure for the enolate is probably more useful for a beginner to draw?
The one that you drew on the page, the first one.
Right. That's right, because that puts the negative charge on the alpha carbon. Now, actually, the textbooks usually prefer drawing the negative charge on the oxygen. Textbooks will usually draw the enolate with the negative charge on the oxygen. But they're both correct, and it's better for a beginner to draw the negative charge on the alpha carbon, because for a beginner, it's more important to show the reactivity. Okay. So those are some things I wanted to review here. Okay. So let's take a look. One thing that you were having a little trouble with was remembering why this was called an enolate. Although you did eventually come up with that explanation. It's because one of the resonance structures looks a lot like an enol. So now we'll look at number 4. Alpha, carbonyl, alpha, beta. Excellent. Good. So there were 2 alpha carbons there. You labeled the carbonyl carbon. You labeled the beta carbon. Good. The one next to the beta carbon could be called the gamma carbon, but that name is not usually used because that's carbon not very interesting. All right, so I'll take a look. Did you have more answers down there, down below? It looks like you might not have finished that question.
Didn't, yeah. Well, I think I would say the role you'd expect these to play in a reaction. The alpha carbon, we've seen it play the role of nucleophile or base in the reaction above, but in an enolate, but this actually doesn't have a negative charge, so it would be more likely to be an electrophile, or not electrophile, but acid. The alpha carbon could play a good acid, and that is because once it loses a hydrogen and receives a negative charge, that negative charge could be stabilized through resonance with that carbonyl.
Good. Okay, that's good. That's good that you came up with that. We haven't quite talked about that particular logic for a while, so that's good that you remembered that. So yeah, these alpha carbons are not nucleophilic yet. These alpha carbons are not nucleophilic yet. These alpha carbons might be acidic, and the explanation you gave was a good one. It was that convoluted explanation. These alpha carbons are acidic because after they lose a proton, they could stabilize the negative charge they would gain through resonance, which makes it easier to lose the proton in the first place. Good. So these alpha carbons could play the role of acids. And then, what would they form? What would be the name of the molecule if the alpha carbons played the role of acids?
If they played the role of acid, then...
What would be the name of the molecule then? What type of molecule?
Enolate.
Then it would be an enolate. And then what role would the alpha carbons probably play in the next step?
Probably a nucleophile.
That's right, because we just did an acid-base reaction. So that's what generally happens in the reactions you'll see in the second semester. First, we're going to deprotonate the alpha carbon, and that will make it into a better nucleophile. Okay, so what role would you expect the alpha carbons to play in number 4?
Acid.
That's right. So that's what I was going for there, and you gave the resonance explanation. How about the carbonyl carbon? What role could that play?
It could be an electrophile because of the delta positive charge, it being next to an oxygen. Well, I guess better than just saying delta positive charge, it's a carbonyl carbon, which makes a good electrophile.
Good. But actually, I like your first explanation. Why are carbonyl carbons electrophilic? Usually we just focus on that delta positive. So what you said was right. The delta positive makes the carbonyl carbon electrophilic. So which one will it be? Will the alpha carbon act like an acid, or will the carbonyl carbon act like an electrophile? Well, you'll just see a bunch of both. You'll see a lot of reactions where the alpha carbon is acidic, and you'll see a lot of reactions in a different chapter where the carbonyl carbon is electrophilic. So it could go either way. You'll just have to learn how to predict it for the particular reactions. You still need a fairly strong base to deprotonate the alpha carbon. The alpha carbon is still not a strong acid, so unless we have a pretty strong base, we're going to use the carbonyl as an electrophile. So that's something I wanted to remind you of. I don't need to be too focused on the alpha carbon. We've been focused a lot on the alpha carbon for the last few sessions because we were focusing on resonance. But don't forget, there's lots and lots of normal reactions where the carbonyl is just electrophilic. There's still plenty of normal reactions where the carbonyl is electrophilic. We looked at many examples of those before. We haven't seen those for a while, but those will still be very important. So those are kind of two different chapters usually in your textbook. There's often one chapter that covers the reactions where the carbonyl carbon is electrophilic, and there's usually a different chapter that covers the reactions where the alpha carbon gets deprotonated. How about the beta carbon?
Not sure. The beta carbon. It seems to be too far from any pi bonds or lone pairs of electrons to have any kind of resonance to stabilize anything, so it wouldn't be very reactive, it seems.
Okay, that's good. That was kind of a trick question, but you kind of came up with the right answer. It wouldn't be very reactive. That was kind of a trick question, and you kind of came up with the right answer. It really wouldn't be very reactive. It's not involved in any resonance, and it's too far from the oxygen for induction to be very important. So it probably wouldn't be very reactive. But wait a second. In question 1, we had a beta carbon that was reactive. So why was the beta carbon in question 1 reactive and not this beta carbon?
Because it had a pi bond, which left it conjugated with that carbonyl.
Good.
And
okay.
That basically allows for resonance to stabilize any charge brought on by a reaction.
Good. So my point with that question was to emphasize beta carbons are not always very interesting. Only the beta carbons that are conjugated with the carbonyl are interesting because only then do we get resonance. Otherwise, beta carbons probably won't have any reaction at all. That's why we never even used the term beta carbon until just our last session, I think. We never even really thought about the beta carbons before because the beta carbons previously hadn't been conjugated, so there was nothing interesting about them. Okay, so a few of these questions, quite a few of these we had some trouble with, or you might have not attacked them using the techniques from the last session. So it's important to review those questions. I'll go back to my screen.
Okay.
Let's see. Okay, so I'd like you to draw the mechanism and predict the products here. Let's try this on your screen. We're going to draw the mechanism and predict the products.
Okay.
How many products did you get?
2 products.
Are those 2 products really different, or are they 2 different pictures of the same thing?
They're different.
Okay, good. I just want to make sure you're checking that. Sometimes you might have 2 pathways, but the 2 pathways might end up giving you the same product, and then you'd want to cross out one of them. So that's just something to check. But in this case, you're right. They really are different. They're not equivalent to each other. Good. Now let's see. In the first step, you ended up, why did you put the positive charge on carbon 3 rather than on carbon 2? Actually, backing up for a second, why don't we fix your numbering? One of your numberings is not consistent with your other pictures. So just for your notes, we should get that right in the top right corner. That, I don't think that messed you up. You wouldn't lose credit for that, but just to make sure that's right for your notes, let's fix the numbering in the top right corner. Remember, the whole purpose of the numbering is to be consistent between the pictures. Okay, you didn't actually make a mistake there, but that's good to be careful about. Anyway, I was asking you, why did you put the positive charge on carbon 3 and not on carbon 2?
Because resonance would allow for more stabilization of that positive charge, it being on carbon, the positive landing on carbon 3, and you are already creating a carbocation, which is pretty uncomfortable for a carbon, and so you would it would be preferred, strongly preferred, to have resonance stabilize that carbocation, which actually means that, like in the case we had before, were that positive charge to end up on carbon 2, there being no resonance to stabilize that leaves it a very, very insignificant product, and so I left that out.
Okay, good. That's right. I noticed, so that I just wanted to, so as you were noticing, we're just repracticing one of the questions that gave us trouble on the homework. I wanted to get this down, so this time you had the correct logic. Notice that maybe this is a better way to do this. One thing that was, I think, confusing you is you've been drawing all 3 pathways completely and then trying to choose which is best. And that's confusing because then you have 2 steps that you have to think about. In this case, you didn't even start the pathway that was insignificant, that was less important. There's no point to even draw the resonant. There's no point to even draw the product that isn't resonance stabilized, and that way we don't start getting confused about whether we're focusing on the first step or the second step. Maybe this is an easier way to get to the same answer as before. We can simply say, if you're going to form a carbocation, should you form the resonance stabilized carbocation or the non-resonance stabilized carbocation?
The resonance stabilized carbocation.
Yeah, wow, isn't that a lot simpler than the way we were explaining things before? Notice that we didn't even have to worry about the rate determining step business. I think that's one thing that was confusing us before. When you think about it that way, you don't even have to get into the business about the rate determining step. You can just say, if you have to decide whether to form, what type of carbocation to form, you want to form the one that's resonance stabilized, not the one that's not resonance stabilized. Just like if you had a choice, you would form the tertiary carbocation, not a secondary or a primary one. Okay. So I think that way of thinking about it is maybe a lot simpler than the way we were thinking about before, which is important because we've been having trouble with this idea. So rather than drawing out the complete pathways and worrying about the rate determining step, we can really boil things down to a much simpler idea. We're forming the carbocation, we want to form the more stable carbocation, so we want to form the resonance stabilized carbocation if possible. Okay, all right, so anyway, I think this time we got that question correct. I'll go back to my screen. Let's try drawing the mechanism and the product for this reaction.
Okay.
Okay. What role did carbon-3 play in the first step?
It was an electrophile.
Good. Why is that reasonable?
Resonance has a structure. There's a resonance structure with a carbocation on carbon-3.
Good. What's the name of carbon-3?
The beta carbon?
That's right. So we've seen that beta carbons are electrophilic. Of course, carbon-1 is also electrophilic, but we've learned who usually gets attacked in these conjugated carbonyls, the beta carbon or the carbonyl.
The beta carbon.
That's right. So you did that correctly. Now, remember that when I gave you a similar reaction in the homework, what you did is you had the deprotonated the hydrogen on the carbonyl. And in this case, that might be even more tempting because this is a strong base. Here we do have a strong base, so it might be even more tempting to deprotonate that hydrogen. But remember, is the hydrogen attached to carbon-1, is that acidic?
No.
In fact, is it reactive?
No.
No. Why do students often think it's reactive? Just because it happened to be drawn, whereas the carbons on the other the hydrogens on the other carbons are not drawn. Remember, that's what we call the aldehyde hydrogen. When there's a hydrogen connected to a carbonyl, that's an aldehyde hydrogen. We said that unfortunately there's this tradition in organic chemistry that whereas most hydrogens on carbons are not drawn, hydrogens on aldehydes usually are drawn. But that confuses beginners because it makes them think the hydrogen is more important than it is. So we know that the hydroxide here is a strong base, but it's still not going to deprotonate that aldehyde hydrogen. In fact, there's pretty much no reactions that involve aldehyde hydrogens. So you did the correct reaction here. Why was it okay to put the negative charge on carbon-2? Carbons usually don't like negative charges.
You're right, but it could handle that because of resonance, which would spread that negative charge over to the adjacent carbonyl.
Oxygen. Good.
Oxygen, yeah.
Now, good. What's the name of the molecule with the negative charge?
It is an enolate.
That's right. Why is it called an enolate?
Because it is basically a deprotonated enol, and 8 just means it can have a negative charge on oxygen, or it does have a negative charge on oxygen, at least in one of the resonance structures.
Now, it doesn't look like a deprotonated enol.
Not unless you move that negative charge up to the oxygen.
Yeah. So the point is, it's called an enolate because there's there's another resonance structure that does look like an enol. Yeah. Okay. Good. So why did we draw this structure? Why did we draw this structure, not the one with the negative charge on the oxygen? Well, as we discussed, I think for beginners, this structure is better because it's usually the alpha carbon that's reactive in the next step. Even though actually most instructors prefer to draw the resonance structure with the negative charge on the oxygen. I think the way you drew it is better for a beginner. Okay. All right, so we just went through this because this was another of the types of questions that had given you some trouble on the homework. So I wanted to review these ideas. This time it looks like we got that correct. Okay, I'll go back to my screen. Let's focus on these oxygens. Would you normally consider these oxygens to be acceptable leaving groups?
No, I don't think so.
Which of these oxygens is the better leaving group?
Perhaps the bottom one.
Which carbon are you thinking of it as leaving? Let's think about leaving like this. So let's think about the oxygen leaving the carbonyl carbon. So which oxygen would be the better leaving group for leaving the carbonyl carbon?
I guess the upper one would, because it would be able to stabilize the negative charge that it gets after leaving with the resonance in that carbonyl.
Okay, that's right. Yes. Okay, so I think that wasn't your first answer, but your second answer was correct. So which of these did you say was the better leaving group, on top or the bottom?
On the top.
That's right. Again, sometimes when you're comparing leaving groups, sometimes you might do that by comparing the pictures before they leave, but it's maybe more common to compare leaving groups by comparing what they would look like after they leave. So it's good that you thought of that idea. We've been talking about that for acids, comparing acids, but you can also use that for leaving groups. Which of these oxygens will be happier after it leaves? The top one. Why will the top one be happier after it leaves? Because it can stabilize the negative charge by resonance. After this oxygen leaves, it'll look like this. And this negative charge is resonance stabilized. Whereas after this oxygen leaves, it'll look like this. And this negative charge is not resonance stabilized. That means that this reaction is easier, which means that this is the better leaving group. It's easier for this oxygen to leave in the first place. Okay, that was just another brief topic. Remember that what we're continuing to do here is we're looking at a bunch of topics from organic chemistry, especially from the second semester now, that resonance can help us to understand. So this will turn out to be a topic that you'll see in the second semester. You'll be comparing these two molecules, and we need to see that this top one has the better leaving group. In fact, because this would probably be a pretty good leaving group because it's resonance stabilized afterwards. Whereas this one, you might be surprised that it's a leaving group at all. Although there are some reactions where this is a leaving group because it's not resonance stabilized after it leaves. Okay. I think that's all I'm going to say about this for the time being. I just wanted to remind you that you can use resonance for many different topics. We've just been briefly using resonance to talk about electrophiles and acids, but you can also use them to compare leaving group ability. You can use resonance to compare leaving group ability. That's something that's resonance stabilized after it leaves is generally going to be the better leaving group.
Okay.
What roles might you expect these molecules to play in a reaction? What role might you expect this molecule to play?
The lone pair of electrons on that nitrogen would enable it to be a nucleophile. It seems like we had discussed that it would not typically play the role of base. Maybe I'm confusing that, but it could be a nucleophile at least with that lone pair of electrons.
Okay, why might you expect it to be a base?
The same reason, the lone pair of electrons.
That's right, and you were confusing that a little bit. What we said is you might have expected, what you were thinking of there is, based on what we said before, you might also expect it to be acidic.
Okay.
Why might you expect this to be acidic? Because there is a delta positive on this hydrogen. The delta positive make you expect it to be acidic, but that actually almost never comes up in organic chemistry. It's only a very weak acid. So in organic chemistry, you're almost never going to see this playing the role of an acid. So you were kind of half remembering that idea. So what we should say here is that based on our theory, this could be a nucleophile because of the lone pair, a base because of the lone pair, or an acid because the hydrogen has a delta positive. But actually, in practice, it's very, very weakly acidic. So you're not going to see any reactions where this acts like an acid. That's what you were thinking of. But it actually is pretty important that this could be a base. It's important that this could be a base. Okay. What I want to focus on here is the basicity. This actually could definitely be a nucleophile, but I want to focus on basicity.
Okay.
Who's the better base here? Molecule A or molecule B is what I want to focus on. Which of these is the better base? How would you think about that? Well,
if it were to act as a base, it would steal a hydrogen. A base donates electrons in order to receive a hydrogen, and so it would leave a positive charge on either nitrogen, and that positive charge would be solely on the nitrogen on molecule A, whereas that positive charge in molecule B could be stabilized through resonance. The benzene ring could actually share the electron density, I guess, through resonance with that nitrogen stabilizing or spreading out that positive charge. So, so molecule B would be preferred as a base.
Let's try to draw that out on your screen. So try to draw that logic out on your screen.
Okay.
That's a very good first step that we talked about before. So you're using kind of a shortcut here. Since what we really care about here is the base and not the acid, you haven't really drawn the full acid. You've used the shortcut and just shown it as H+. So that was a good idea in this case, just to show the acid as H+, just so you can kind of show how the positive charge ended up on the nitrogen. So that's a good place to start. Good.
Okay. That looks weird. On second thought, I think he's got his octet full. I don't think we can actually add that pi bond to it. what I was going to draw would be that, and then that would actually resonate around, spreading out that positive charge. But it looks like this nitrogen already has a full octet, and so it does not look like it would have that resonance.
Okay, that's right. So notice how it's important to actually draw the resonance structures. We've been getting a little bit sloppy and doing a lot of the resonance in our heads. Maybe we shouldn't have done that, because you can see sometimes you can fool yourself into thinking there's resonance when there isn't, right? So you can see how it's important to actually draw it out. Your second thoughts were your better thoughts here. Your second thoughts were your better thoughts. It's good that you saw that once you started to draw it out. If you remember, that's one of the main things that we learned at the very beginning of resonance: don't exceed an octet. And so it's good that you caught that. Does the nitrogen with the positive charge have an incomplete octet?
No.
No. Remember, generally only carbons with positive charges have incomplete octets, not nitrogens. You can see it doesn't make any sense, because if you drew that resonance structure, the nitrogen would have 5 bonds. And certainly a nitrogen can't have 5 bonds. So, are there resonance structures to stabilize that positive charge?
No.
No. There is another resonance structure, but it doesn't spread out the positive charge. You could move the pi bonds around the ring, but that doesn't do anything to stabilize the positive charge. So there are no resonance structures to spread the positive charge onto another atom. So it looks like our first logic turned out to be incorrect. Our first logic here was incorrect, because there is no resonance that spreads out the charge after the nitrogen gains a proton. So, all right, so the lesson here, that's good that you caught that when you started drawing that out. That's good that you saw the nitrogen did not have an incomplete octet. So anyway, one lesson here is it's important to actually draw resonance structures, usually, rather than just kind of visualizing them in our heads. So we'll have to try again. It turned out that way of thinking about things didn't work. So let's try again. Try again to figure out who's more basic. Who's more basic, the top molecule or the bottom molecule? How can we figure it out if that logic didn't work?
Well, I suppose if you were to look at it not as the product side, you could look at it from the reactant side, and in that case there would actually be resonance, where this lone pair of electrons could form a pi bond, leaving the nitrogen not positive, but with the pi bond. So in there. That would leave negative charges throughout the ring. And perhaps, actually, it looks like this would be an orthopara director for the benzene to act as a nucleophile or base. And in that sense, it seems like I'm not quite sure what the logic would be, but you have 4 atoms that could potentially act as bait.
Okay, so let's go back. That first resonance structure that you drew was incorrect. Or, yeah.
Did I do it wrong?
Yeah. So let's erase that next set of arrows that you've drawn. We're not ready for that yet, because that picture is incorrect. Check your work there.
Oh, I guess it was supposed to have a positive charge.
How do you know?
It's at the tail end of electron-pushing arrows, which makes it one step less negative, or one step more positive.
Good. And it started neutral. Remember, there's that two-step process. Okay, that was a very important mistake that we just made there. Remember, what's the most important factor in organic chemistry?
The charges.
The charges. What's the whole point of drawing this resonance? The whole point of drawing the resonance is to find the hidden charges. So that might seem like a minor detail, but that actually turns out to be a very serious error to leave out that positive charge. That's something that's given us a little trouble in the past. Do you remember we've talked about this? This is actually the most common mistake students make with electron-pushing arrows, both on resonance and mechanism. So let's review that one more time. The most common mistake, or one of the most common mistakes students make, is that when the arrows start on a neutral atom, they forget to make the atom positive. One of the most common mistakes students make is that when the electron arrows start on a neutral atom, they forget to make the atom positive. So we really have to watch out for that. Do you remember what's the technique we've talked about to avoid that? Well, the technique is you just need to remember on every step of every mechanism, or every time you draw a new resonance structure, how many charges should you change?
2 charges.
And so I think we've talked about how you have to build the habit of always asking yourself, what 2 charges did I change? Looks like we haven't quite built that habit yet. That's one of the most important things from all the work that we've worked on together, is to make sure you're always changing 2 charges. Why did you not change the charge here? What do students do instead? Unfortunately, like I mentioned, a lot of students get into the habit of just drawing what feels good, or drawing what they expect to see after the arrows. They don't really use the arrows to draw the product, and that very often means they end up losing that positive charge. So remember, this is hard for students to do, but don't draw the picture that feels okay or that you expect. Draw it based on the arrows. I guess the reason why this is hard is because we're drawing so many pictures. It's hard for people to take every picture seriously. People start, people get comfortable, and they just kind of draw. They say, oh, I kind of know what to expect here. You have to kind of really force yourself to treat every single situation as a new problem, and draw what the arrows are telling you to draw. And just force yourself to always make sure you're changing 2 charges. All right, like I say, that's a pretty consequential mistake, so we have to watch out for that. I think you might have forgotten a little bit what we were trying to do here. What were we trying to do with this molecule? What was the question originally?
Which is the stronger base?
That's right. It sounded like you had kind of forgotten that. So we want to use this resonance to decide who's the stronger base, if possible.
Sure. Well, because the second molecule with the benzene ring has more resonance stabilization, more resonance structures to spread out the formal charge. Well, to spread out electron density, because I guess it didn't start with the formal charge. Because of that, it is more stable than the first molecule, and would be less reactive.
Okay, now there's a lot of truth to that. There's a lot of truth to that. Rather than thinking directly about the stability, remember, what's the most important factor in organic chemistry?
The charges?
The charges. So rather than using that stability, or rather than comparing stability, let's try to use the charges to get to the answer here.
Okay.
Remember, the question is, who's more basic? Which nitrogen is more basic?
Well, the first molecule doesn't have any kind of charges except perhaps some delta positive charge, which does not help its basicity. But the second molecule has resonance structures which reveal formal charges, specifically negative charge within the benzene ring, which would leave it potentially basic on the ortho and para carbons.
Okay, good. Now, remember what we were trying to compare is which nitrogen is more basic.
Oh, okay.
The question
So,
is which of these nitrogens is more basic.
well, the nitrogen in the first molecule would definitely be more basic than the nitrogen in the second molecule, because the first molecule has a lone pair of electrons, and that's it. The second molecule has a lone pair of electrons, which is not always there throughout the resonance structures. It's got a positive charge, a formal positive charge on some of the resonance structures. So that usually, well, pretty much always says that it's not going to act as a base if it has a resonance structure with a positive charge.
So who's more basic?
The first nitrogen on
Right.
that first molecule.
Okay, good. Now, actually, I just realized something I said before was mistaken. I guess you were actually getting the right answer before with your first logic in terms of stability. You first tried to analyze this in terms of stability, and you actually did get the right answer there. So maybe I shouldn't have discouraged you from that. But I think I think you were maybe overcomplicating things. In this case,
Okay.
it's so actually your first logic, your first way of thinking about it would have gotten you to the right answer in this case. But I think the second way is simpler. We can simply say because there's a hidden formal positive charge on the nitrogen, that makes it less basic.
Okay.
That hidden there's a resonance structure where the nitrogen has a positive formal charge that makes it less basic. Therefore, the first molecule is more basic.
So overall, the molecule as a whole, would one molecule be more reactive than the other?
Let's see. I don't know. I don't know what the answer is to that myself. I don't think you wouldn't be given a question just to compare reactivity in general here, and I'm not quite sure what the answer is. You did notice that the ortho and para positions here are somewhat basic.
Yeah.
I think it's still, though, it's actually still the nitrogen that's more basic than those positions.
Okay.
Although that might be a little hard to predict, but that's something you might just have to memorize. So
Okay.
I think that if the bottom molecule did act like a base, it would still be the nitrogen that was the base, rather than the carbons. I don't know.
Okay.
Maybe that's not even right. Let's see. That's probably right, because if the carbons were to act like a base, you
Yeah.
would lose the aromatic structure of the benzene. That's something we haven't talked about very much. But benzene has an aromatic structure with the 3 conjugated bonds that you would lose if you just protonated at the ortho or the para positions. So
Yeah.
it turns out benzene can sometimes act like a nucleophile or electrophile, because this is getting a little complicated. If you remember, we saw like electrophilic aromatic substitution, where benzene can act like an electrophile, because that's a 2-step reaction where it eventually gets back to being aromatic. It gets back the 3 double bonds. When we went over those reactions, we saw they were 2-step reactions. First, the benzene acts like a nucleophile to attack an electrophile, but then there was a second step where it got back the double bond and became aromatic again. It's been a while since we discussed that. But we saw that if the benzene acts like a nucleophile or electrophile, there's ways for it to get back the double bond in the second step. Benzene never acts just like an acid or a base, because if it did that, it would just lose the aromaticity, and there wouldn't be any logical way to get that back without just undoing the acid-base step. Okay, so there's no point protonating the ortho position. There's no point protonating the ortho position, because then the only way to get the double bond back would be to deprotonate the ortho position, and then the reaction would just have been reversed. Okay, well, I don't want to get too complicated here, but in this case, so I think it would be the nitrogen in both molecules that would be basic, but the nitrogen in the second molecule is not very basic because of the positive formal charge.
Okay.
Okay, so this got a little complicated here because we made a mistake, and also I said I made a mistake at one point. I said you were on the wrong track. One thing you said actually did give you the right answer. But anyway, the best way to think about this is with the formal charge. Notice the one thing that was giving us trouble here is, as I've discussed, oftentimes when you're trying to compare reactivity, there's 2 ways to do it. You can compare reactivity by comparing the starting materials, or you can compare reactivity by comparing what the molecules would look like after the reaction. And sometimes it's not obvious which way works best. When you were comparing the basicity here, you started by trying to compare what they would look like after they gained protons.
Yeah.
But it turned out that didn't really work in this case. It wasn't obvious. It was a good thing to try. But it didn't turn out to work very well because it turned out there wasn't really any resonance stabilization of the positive charge in either. So then when I asked you to try again, you had a good idea. Then you compared the starting materials. That was a good idea that you've worked out. So just keep that in mind. You have to use judgment to decide whether it's better to compare the starting materials or the products. And sometimes it's not obvious and you just have to try both ways. Sometimes you can get the same answer both ways. Sometimes you can do it either way, but sometimes you can only do it one way. Or sometimes one way is clearer. So in this case, it's better to compare the starting materials. So again, this is another example of using resonance. We've used resonance in the past to compare who's the better leaving group or who's the better acid. I don't think we've seen many examples where we used resonance to compare who's the better base. So this is a good example of that. This is again something that's likely to come up on the DAT or in your course, comparing basicity. So again, we can use resonance here to make that comparison. One thing I would point out is remember that at first you were trying to use the resonance in the product to explain things, and that actually would have given you the wrong answer. Your first answer was actually incorrect when you were trying to use resonance in the products. So that just shows the importance of thinking clearly through the steps here. I think at first you thought that the second molecule was more basic, but that logic turned out to be flawed. In fact, the top molecule is more basic if you look at the resonance in the starting materials, not in the product. Okay, let's see. One thing I would say is when you're comparing acids, it's usually best to compare acids by asking what they look like after they lose the proton. When you're comparing bases, it's usually best to compare them by comparing the starting materials. Those are just rules of thumb. There's exceptions to that. But most of the time when you're comparing acids, it's usually done by comparing the products. As you mentioned before, the way that's put technically is you compare the conjugate bases. When you're comparing acids, you usually compare the conjugate bases. Whereas when you compare bases, you usually just compare the bases. Like I said, there's exceptions to that, but those are some rules of thumb. Okay. That certainly applied in this case. Comparing these bases, it was better to compare them before rather than after. Okay.
Great. Thanks.
Oh, but the most important thing, let's stay on your screen for a second.
Yeah.
So when you did this the second time around, you did something right and you did something wrong. The thing that you did that was right is you were looking for resonance before the reaction. Yeah. But that wouldn't have done you any good because you left out the positive charge, right? Remember, I was making a big deal about that. You can see now why I made a big deal about that. If you leave out the positive charge from the resonance, that defeats the whole purpose of doing the resonance. The whole point of doing the resonance was to discover that hidden positive charge on the nitrogen. Since you had left that out, I don't think you were going to get the right answer using that approach. So that's the most important thing here. More important than this specific example. Remember, students have a very hard time remembering that when there's a neutral atom at the beginning of the arrows, it gains a positive charge. That's a very common mistake, and it's kind of a catastrophic mistake to be dramatic about it because the charges are so important. So remember, one way to avoid that is try not to get into a groove too much or to get too comfortable. Try not to draw what you expect to see. Make sure that you always ask yourself, every time you use electron-pushing arrows, what are the two charges I'm changing? You just really have to force yourself to really be in that habit. What are the two charges I'm changing? This is kind of like athletics. You know, like when you're doing athletics, there's habits that you have to build that you always do every time. Like, I don't know, if you're playing tennis, you try to force yourself to follow through on every swing until it becomes automatic. So for every swing, you have this pattern that you go through where if you've done it correctly, the racket ends up on a follow-through. Well, in organic chemistry, we have to build these habits too. The follow-through here is to make sure that you've changed two charges. You need to make sure you've changed two charges on every step because otherwise we get the charges wrong. And like I say, that's a catastrophic mistake. All right, so I'll go back to my screen. But that was the most important issue there. I'm making sure we've changed the two charges. Let's see. What roles might we expect this molecule to play?
Base or nucleophile?
Excellent. Yeah. Could be basic or nucleophilic, as we were just talking about. What makes it basic?
The lone pair of electrons on the nitrogen.
And what makes it nucleophilic?
The same lone pair of electrons on the nitrogen.
We saw that theoretically you might have expected it to be acidic, but it's really not very acidic. Let's focus on its basicity. Let's ask which of these nitrogens is more basic. So now I want to compare these two molecules. Let's decide which of these molecules is more basic.
It looks like the resonance, I'll go ahead and draw that out, but it looks like the resonance would reveal a hidden positive charge on the nitrogen on the right, which would make it not very basic. Yeah, so the more basic would be the first molecule.
So this turned out to be kind of similar to the previous example, and you went through the correct logic here. It turned out in this case that it was more useful again to compare the starting materials rather than the products. Because there's a hidden formal positive charge on the nitrogen from resonance, that makes it less basic. This is similar logic to before. Good.
Okay.
Good. That's the right way to think about that. I'll go back to my screen. So incidentally, this molecule is called an amine. When the nitrogen is connected to a carbonyl, it's not called an amine anymore, it's called an amide. These will be important terms to memorize in the second semester. You don't necessarily have to memorize them right now. These will be important in the second semester, though. Notice they sound similar, so it's easy to get them confused. So the important thing is, are amines basic?
Yeah.
But amides are usually not basic. That's one reason why they get different names. They get different names because they have different reactivity. Actually, for that matter, what role did we expect the amine to play?
Base or possibly a nucleophile?
Yeah, so let's compare the nucleophility too. Which of these is more nucleophilic?
We're talking specifically about the nitrogen, right?
That's right. That's a good point.
The amine would still be more nucleophilic for the same reason, because a hidden positive charge would be on one of the resonance structures of the amide.
Right. So in fact, this nitrogen is for practical purposes not nucleophilic. Or basic, because of those hidden positive charges. That's why these get different names, even though they look similar. The reactivity for amines is quite different than for amides. Amines are nucleophilic and basic. The nitrogen is. But amide nitrogens are generally not nucleophilic or basic. You wouldn't expect that from this picture, but the resonance has revealed the hidden positive charge that explains that. So incidentally, what reactivity would you expect maybe from an amide? Which atom would react?
The oxygen. Seems like the oxygen would be a good nucleophile or base.
That's possible. What other atom might be reactive?
Oh, the hydrogen on the nitrogen could be acidic.
That actually is possible. That is possible. Why would this hydrogen be more acidic than this one? We said these hydrogens are really not very acidic. Why would this hydrogen be more acidic?
Because of the positive charge on one of the resonance structures.
That's right. So you can compare the starting materials, because does a positive charge make this nitrogen more or less basic?
The positive charge makes it less basic.
But more or less acidic.
More acidic.
We said that this is really not very acidic at all, but this actually is quite a lot more acidic. All right. So yeah, that's a good point. I wasn't going for that, but that's a good point. This hydrogen now is more acidic. It turns out that reaction usually is not covered in the course. That's a real reaction that some courses cover, but most courses don't pay much attention to that. So I won't emphasize that. Theoretically, so it really is true. There are some reactions where this hydrogen is acidic that some ochem classes cover. Your class probably won't cover that, though, so I won't make too big a deal about it. But your logic was correct there. Your logic was correct. There's another atom here, though, who's very likely to be reactive. What's the other atom here that might be reactive that we haven't mentioned yet?
Carbon 2.
What role might it play?
You might play the role of electrophile.
Yeah, and why is that reasonable?
Because it is carbonyl carbon. It has a delta positive charge.
That's right. In practice, have we seen many reactions where carbonyl carbons were electrophilic?
Yeah.
So that should have been one of the first things that we thought about here.
Okay.
Because this carbonyl carbon, well, I don't know. Actually, all right. Actually, this whole molecule is actually not that reactive. This molecule is not that reactive overall. I don't want to get too complicated here. You might expect the carbonyl carbon to be electrophilic because of the delta positive. Amides are really not very reactive, but we don't want to get into that too much. You might expect the carbonyl to be electrophilic because of the delta positive. The oxygen might be basic. Usually the oxygen will not be nucleophilic, even though your logic made sense. You thought the oxygen might be nucleophilic because there is a resonance structure where it has a negative charge. That seems to make sense, although there aren't really any reactions where that happens. Okay, well, maybe I shouldn't have gotten into that too much. That was getting a little more complicated than we need to get into. So the main thing I wanted to focus on here is that the amide is not nucleophilic or basic. This amide is not nucleophilic or basic because there's a resonance structure where it has a positive charge. It's also interesting to notice that this nitrogen is more acidic than this one. There are reactions where this is acidic because of the positive charge, although most courses don't cover those, but those are real reactions. Okay, all right, so in any case, those are some of the key points there.
Okay.
This is a tough one. And this would be a tough one to figure out, but I'll give you a shot. Try to predict the reactivity here. These are 3 phenyl groups. Do you know what a phenyl group is?
Oh, okay. It's probably kind of sad. I was looking on the.
Oh, you were looking for the element. Okay, yeah. No, this is not some bizarre element. These are 3 phenyl groups. Those are. Do you know what a phenyl group is?
A phenyl group is like a. It's a benzene ring with an alcohol group coming off of it.
Actually, that would be phenol.
Phenol. Oh, okay.
It's hard to pronounce, but these are phenol, which means they're basically just benzene rings.
Oh, okay.
These are just benzene rings. I'll give you a hint. The benzene rings actually turn out not to play any role here. The benzene rings are not playing any role. That's why they're being abbreviated. So this is a reagent you'll see in the second semester. This is a reagent you'll see in the second semester. I'll give you a hint. It's either 2 or the phosphorus. So let's try to figure out what role carbon 2 or the phosphorus might play in a reaction.
Okay.
To be even more specific, let's figure out what role carbon 2 might play. What role might carbon 2 play in the reaction?
Carbon 2, it looks like it could play the role of nucleophile.
What was your reasoning there?
It has a pi bond. Well, no, I was thinking of an alkene.
Right.
Carbon 2, well, So the phenyl groups could they have any resonance relationship?
They probably would, but my hint was that the phenyl groups are not going to play any role here.
Okay.
We don't need to really think about the phenyl groups to get the answer. So what we need to do here is try to draw another resonance structure.
Okay.
Involving carbon-2 and the phosphorus. The phenyl groups will turn out not to play a role. So can you think of a way to draw a resonance here that involves carbon-2 and the phosphorus?
Well, I'm a little unsure. It seems that they're very similar in electronegativity, carbon and phosphorus.
Okay. Who would you expect is more electronegative?
Perhaps phosphorus, because it's further to the right.
That's usually what works in organic chemistry. So I think phosphorus is more electronegative because it's further to the right. However, this is tricky. So the question is, should the electrons move towards carbon-2 or towards the phosphorus? This is tricky because there's a new thing here. Did you notice how many bonds does this phosphorus have?
Has 5.
Right, that's more than an octet. So that should make us worried. How is that possible? Does that mean this is an illegal picture? Is it possible for phosphorus to have 5 bonds?
No, it's it is possible because it's in the 3rd period, and those
That's right.
atoms can have more than the regular octet.
So that's why this picture is possible. So this is a possible resonance structure because the phosphorus can have an expanded octet because it's in the 3rd row. But the way you should think about it is it's not thrilled. In a way, it would kind of prefer to have just an octet, or there's some advantage to have the octet. So the other resonance structure, is the next resonance structure going to move more electrons towards the phosphorus or move electrons away from the phosphorus? Does the phosphorus have too many electrons or too few?
I guess it would move them away if it preferred having just the octet.
Yeah, it does. It has more than an octet now. So
yeah.
The other resonance structure would be the one that just gives it an octet.
Okay.
Notice that that's the opposite of what electronegativity would probably predict. That's why I said this was a hard one. This would have been a hard one for you to figure out because we haven't used that logic before. But I wanted to go over this because this is an important reagent in the 2nd semester anyway. So normally you might expect that the pi bond would move towards the phosphorus because it is more electronegative than the carbon because it's further to the right in the periodic table. But the more important factor here is that the phosphorus has more than an octet. That's possible here, but it's not thrilled about it. So the other resonance structure should be the one where we move electrons away from the phosphorus to give it an octet.
Okay, so that would leave...
Notice the phosphorus is not thrilled in either picture. Now it has a positive charge. That's not too happy about that either. So neither picture is hugely happy, but these are the 2 significant resonance structures. These are the 2 significant resonance structures. The one thing we don't want to do is move the electrons towards the phosphorus because it already has kind of too many electrons in the first picture to start with because it had that expanded octet. Okay, that would have been hard to predict because we haven't really used that logic ever before, the expanded octet. But this is worth seeing because this is an important reagent in the 2nd semester. So now, based on that, what role would we expect carbon-2 to play in a reaction?
Nucleophile or base.
That's right. It turns out what it actually acts as is a nucleophile. All right, so there's one important reaction in the 2nd semester where carbon-2 acts like a nucleophile. So I just wanted to use this as another example of resonance.
Okay.
So we can use resonance. This is, you don't need to memorize this name right now, but this is what's called a phosphorus ylide. And this phosphorus ylide has a reaction in the 2nd semester called the Wittig reaction. You don't need to memorize those names right now. But anyway, that's an important reaction in the 2nd semester. Anyway, we were just trying to look at a bunch of examples where we use resonance in the ochem class, so this is one I wanted to mention. So this is kind of a weird example because normally you would move the pi bond onto the more electronegative element. Normally, and that's kind of what you were thinking, normally you would move the pi bond to the more electronegative element, but in this case, because the phosphorus already had more than an octet, it's actually more significant to move the electrons away from it. And then we can see that it's actually the carbon that's nucleophilic here. Okay. So that's just an example to take a look at. Okay, so, all right. So that pretty much covers what I wanted to talk about for resonance now. We've looked at a bunch of different practical applications of resonance. I think we made some good progress on that. On the other hand, I think we might also have started to slip a little bit. There have been a few cases here where we forgot maybe the most important thing, which is changing the two charges. So remember, more important than any of the details we've gone through, all of these details here were just to practice kind of drawing resonance. So the most important thing from all of this is to always change two charges for every new resonance structure. We always need to change two charges, and then the resonance can show us the hidden charges. So we've seen a bunch of different examples of how that comes up.